Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software RFEM as well as RWIND Simulation. The topic for today's webinar is RWIND Simulation, Wind Load Simulation, and Generation. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be today's moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. I always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So as far as the content over the next hour today, I want to give a brief introduction to our brand new program that we just released called RWIND Simulation and the theory behind it for CFD wind analysis. Then we'll move on to our example where I'll give a quick review of our initial 3D model within our finite element analysis program, RFEM, which will work concurrently with RWIND. Within RFEM, we can set up the RWIND settings and parameters for the CFD analysis. And as of last week, we released RFEM version 521.02, which includes the ASCE7 wind profile, which we'll be taking a look at today with our example. Then we can run a wind load case within RWIND, which is within a numerical wind load tunnel. From here, we'll review the wind load results, and then finally we can export these wind load forces back to RFEM to continue the analysis and design of our structure per usual. So RWIND Simulation has actually been a joint collaboration between 3 companies over the last several years, and this includes Delubal Software, as well as PC Progress and CFD Support. The program utilizes a CFD numerical analysis, and this stands for Computational Fluid Dynamics. What we're doing here is to simulate fluid flow around the structure in a numerical wind tunnel. We currently utilize the OpenFOAM CFD solver, but there will be many more solvers in development, and we'll release those as we come out with them. In particular, this OpenFOAM solver in RWIND is called RWIND Simulation Solver. It is for steady state for incompressible turbulent flow. It utilizes the simple algorithm, which stands for the semi-implicit method for pressure-linked equations. Now we have much more information behind the theory of the program that's available in our RWIND manual on our website. But ultimately, we're going to run this calculation in order to get the 3D velocity fields and pressures within the entire wind tunnel. Then from here, what we'll use is the exterior surface and member pressures on the structure to calculate the wind load forces. So when it comes to the CFD finite volume mesh, this is a pre-processing method that is extremely time consuming. We must ensure that all mesh edges have exactly 2 adjacent triangles, that triangles cannot overlap each other, and that model boundaries must be closed. So an engineer might find themselves spending a significant amount of time just creating this volume mesh. So one of the main goals for this program was to improve this functionality without sacrificing quality of the analysis itself. And we do this with what's called a model simplification, and this will automatically correct problems that may have otherwise occurred by manually creating this mesh. The simplification includes a special mesh shrink wrap that we're applying around the structure. So if we take a look at the various points we're going to address with this simplified model and the mesh shrink wrapping, the first is to eliminate details that are not relevant to the simulation. And a perfect example of this is these 2 flower models over here on the upper right. You'll notice with the note number 1 here, we're pointing to the inside of these flowers that have quite a bit of detail going on. Well, by simplifying this detail, we'll go ahead and simplify the model, create a better mesh, but it won't sacrifice our wind loads on the structure. And essentially, these details are not important. Number 2 is to address the intersection of triangles, and this is denoted by point number 2. Remember that I said that each mesh edge has to have exactly 2 adjacent triangles, and triangles cannot overlap each other. So you can see by point number 2 that this is not the scenario here, so this is not an ideal mesh. Number 3 is to address open edges and apply zero thickness surfaces. So we have these open edges indicated around the exterior of this flower as well as down on our building here for our next example. So what we can do with these complicated open edges is just simply apply a zero thickness surface to simplify that model further. And number 4 is to close the openings to prevent interior airflow. Well, this is best explained, which we can see here in our example on the right, is window and door openings. Obviously, within the FEA model itself in RFEM, we are not going to model glass panels or actual doors over these openings because they're not important for the structural design. So when it comes to wind analysis, though, we don't want to allow interior wind flow where it shouldn't be occurring. So we want to close these openings with that shrink wrap mesh. So within our wind, we're going to address each one of those points, 1 through 4, with that shrink wrap. Again, I mentioned that we're going to eliminate details that are not important, and we can see that with the same 2 flower models on the right. We've now eliminated the detail at the center of the model, but yet this isn't going to affect the CFD analysis and overall wind loads enough to matter. So by simplifying, we can decrease the overall mesh. Number 2 is the intersection of triangles. Again, each mesh edge has exactly 2 adjacent triangles. The mesh on the left is pretty fine. The mesh on the right is quite a bit more coarse, so we can see exactly how those triangular mesh elements are lining up adjacent to each other. Number 3 is to close the open edges. Again, this model on the right, we can add a zero thickness surface here to close those open edges and simplify further. And number 4 is to close openings to exclude airflow where it doesn't exist, which we can see with our building model down at the bottom. We've closed all those window and door openings. Now, there is a very important assumption, and the assumption is if this simplified model approximates the original model well, then the calculated wind loads are going to be correct. This is really no different than and making sure that our mesh is refined well enough so that we get accurate results. Same concept for the simplified model and mesh shrink wrapping around our structure for CFD analysis. The user has the ability to control the opening size, so we can close smaller openings while leaving larger openings open if we'd like, as well as the mesh size. How coarse or how fine do we want this mesh? And we'll see all that with our example today. There is the option to turn off the simplified model, but this really is only suggested for advanced CFD users. So most of us on today's webinar will always leave this option checked. I'll show you that in the example as well. So a very common question that we have been asked since we have released this program is the role of CFD with engineering standards. So I just want to spend a few minutes talking about this discussion point. The engineering codes such as the ASCE 7, the NBC, the Eurocode all provide minimum engineering requirements and loads for safety considerations. And of course, this includes wind loading. Well, when we take a look at the ASCE 7 and the various wind load methods, this includes the simplified method. So for any simple structure, the analytical method for any more complex structures, and finally we have the wind tunnel method, which is for structures that don't fall within these simplified or analytical methods. And you'll notice that I did not mention CFD in this list. So the question might be, well, how can we use CFD then when it's not necessarily listed within these standards? How can it still be a useful tool? So that brings me to my next slide here, where I'm going to discuss several points on how we can use CFD as a cost-effective engineering tool for many useful applications. Now notice that I have underlined tool. We really are not looking to replace the standard and the minimum requirements, but rather how can we utilize this along with the standard to better narrow our focus on how wind loads will affect our structure. And the first point here is to assess varying wind loads early on in the design process. So maybe we can get a preliminary design on our complex structures just to determine if wind is controlling. Just an idea so that we can save money, save time early on in the design process rather than determining much later on that maybe wind loads are affecting our structure a bit more. It's also known that the standards only provide minimum wind loads. It's ultimately up to the engineer whether he or she should increase these loads, which may be necessary due to special or complex cases. So for example, if we have very unique structure geometry, and yes, the code is going to give us minimum design loads, but there are scenarios where wind loads may need to be increased. And again, that's up to the engineer, and we can use CFD as an analysis to determine if we do need higher loads. The third point here is a really important one, that we hope that RWIND can be used for structures which fall completely outside the standard, where there are no minimum guidelines to follow. What this ultimately leads to is engineers guessing, estimating, assuming wind loads, when in reality that particular structure is nowhere to be found within the ASCE. A perfect example of this is a lot of fabric and tensile tent type structures. So again, using this as a tool to have a better understanding of the wind loads that should be applied that fall outside of the ASCE 7 specifications. Another interesting point is surrounding terrain considerations. So often projects are located near hills or have adjacent buildings that will affect the wind flow. And yes, it's very clear that there are factors and coefficients in the code that address these considerations, but keep in mind that those factors and coefficients are just general guidelines to encompass all projects, and they are not specific to your particular project. So if there's an adjacent building, which we'll see in our example today, that we know is going to significantly impact the wind flow on our structure, perhaps we want to take a closer look at this. Another great point is that we can use CFD in a numerical wind tunnel to run a preliminary analysis before we run our wind tunnel testing, which is covered in the ASCE 7. This is going to lead to cost and time savings. If we can quickly throw this structure into a CFD numerical wind tunnel, we might see that our structure is completely over-designed or completely under-designed. This allows us to make those changes before we're spending the money and the time to create this smaller scale structure to run in an actual wind tunnel. The second to last point is determining occupant comfort with applied wind loads. So again, the code is here to address safety concerns, but for people's threshold and maybe what is uncomfortable when you're inside the building, this isn't necessarily addressed directly within the standard. So it could be an idea to run this in the CFD program to see, okay, that maybe we need to increase the design of our structure a bit to make this a little bit more comfortable for our occupants. And finally, I want to make the point clear that these complex CFD methods are for complex structures with no standard guidelines. We are not promoting this program to be used with completely rectangular structures. I think we're all in agreement it's easy enough to flip open the code and to get those minimum design wind loads. But again, these are for the structures that we can't so easily refer to the code, and we really have no idea how our wind loads may impact. So that's what we really want to promote our RWIND simulation for. Okay, so that is enough behind the theory. What I want to move on to is our example today and how our RWIND simulation works with our finite element analysis program, RFEM. So we will begin today modeling our structure completely within RFEM. And this includes surfaces, members, and solid elements. So today's example is only with surfaces, but just keep that in mind that RWIND can definitely handle members and solids as well. So essentially any structure is possible. We also can set up our various load cases, so dead load, live load, snow load. But when it comes to our wind load case, this is where we're going to export the structure geometry into our RWIND simulation. Here is where we run the CFD wind analysis. And then we can import in those wind loads back to RFEM. Now we have a typical load case for wind that we can combine in our load combinations within RFEM. So wind along with dead load, live load, snow load can all be considered together, and we go about our analysis within RFEM as usual. And eventually we can move into the design add-on modules. So that's a little background on the theory and how essentially the programs will be working together. So what I'm going to do now is to get started with our example today. You'll notice here that I have modeled a very simple but interesting geometry here for our structure within RFEM. Now, for any of you joining us today from New York City, this structure may look familiar. What I have modeled it after is the building located in New York City called Via 57 West. And you'll notice how interesting the geometry is. Obviously, first we have this triangular type structure, but even more interestingly enough is that we have this huge opening right here in the center. And this goes all the way down to the courtyard at the base of the structure. So although it may be applicable to refer to the standard to get minimum design wind loads, I would certainly say that the standard does not address a building with this type of structure geometry, especially with this large opening in the center. So that's essentially what I have done here. You'll notice that I created this structure and it's very simplified. I didn't add any windows, doors. The interior of the structure is not modeled. It's just to get the overall basic geometry. And we can see that I've modeled this with surface elements. We have double curvature at the front of the surface. And I've taken into consideration the large opening right here in the center. So this is just the basic geometry of our structure. Now I've also set up a single load case here for self-weight. And I haven't created any other load cases quite yet, but let's move into our first wind load case scenario. Under Calculate, I can access our wind under our RWIND simulation where we can simulate and generate wind loads. So this brings up my dialog box here that I'd like to go through in a little bit further detail in order to set up our parameters for our CFD analysis. The first is to define the wind directions. You'll notice that the program automatically sets a uniform step here. So if this is set to 45 degrees, you'll notice that every single direction is defined here, 0, 45, 90, and so on. We could change this to 90 degrees, and now we have only 4 defined directions. You'll notice that on the second tab here, this lists out the individual load cases. So we have wind in the 0 degree direction, 90, 180, and so on. Now in turn, if you just have a few different scenarios that aren't necessarily defined at each one of these steps, we can manually define the direction. So let's say I want 35 degrees and 135 degrees. Well, again, on this second tab here, we can see that both those load cases are automatically updated. For today, we'll take advantage of 90 degrees and we'll actually be looking at only one load case direction in particular. The model properties, so this allows us to close those openings. And remember in the PowerPoint, I said the user has the ability to close the opening size that they define. So in this example today, I don't have any openings necessarily, but if I did, I could enter in some values here to close windows and doors. We do have an extremely large opening in the center. I certainly don't want to close that because I want the wind flow to be allowed to move freely within that area. So for today, again, we'll just leave this as 0. Now the terrain level, if we had modeled a basement for our structure and we do not want that basement height to be exposed to the wind profile, we could set the depth here. So for example, if we had a basement that was 30 feet in height, we can type in 30 feet and now the wind profile will be applied at the elevation of 30 feet and above. We don't have a basement for today, so we can leave this unchecked. Then we have the wind velocity where we can define our wind parameters according to a couple standards here. We have the Eurocode available to us, and just last week we have released the ASCE 7 2016. Now, if you are utilizing a standard which is not found here, such as the NBC code or something other than the ASCE 7 or Eurocode, it's no problem because all you need to do is to define this user-defined option. What this can allow you to do is to simply define the wind profile, including the wind velocity as a function of the height. You can import and export directly to and from Microsoft Excel, so that might be quick just to generate up a quick spreadsheet, import in those values here. Now we will have more standards in development and release as they come out. For today, we do want to take advantage of the ASCE 7. The first option here is the exposure category, and this comes from section 2673 within the standard. We have here either exposure B, C, or D. We're going to choose exposure D today because this building is actually located right next to the Hudson River. So D is for unobstructed areas and water surfaces. We don't have much blocking that wind coming off the Hudson River, so we kind of want a worst case scenario here. The topographic factor, which is KZT, comes from section 2682, and this is the wind speed up effect. We'll actually just be using the default 1.0 here. Ground elevation factor, KE, comes from section 2610.1, and this is in reference to the ground elevation above the sea level where our project is located. Again, we'll be using 1.0 for our project today. Now, the basic wind speed, you'll see here that this is defined as a velocity in feet per second. This information should come directly from the ASCE 7 and the wind load maps. What might be helpful is to take advantage of our GeoZone tool on the DeLuBal website. So you can find this tool at delubal.com. Under Solutions, you'll see the GeoZone tool available to us under Online Services. What we've done here is we have considered all of the loading maps for snow load, wind load, tornado, as well as seismic directly from the ASCE 7 standard. We have synced it with Google Maps. So all you need to do is just to type in your address and hit search. The program will give us the relevant values from the ASCE 7. So for our example today, our address is located at 625 West 57th Street. You can see the program automatically determines that this is located in New York City. We can use our zoom function here to zoom in all the way to where our project is located. We can even turn on the satellite view here, and sure enough, we can see our structure via 57 West located right here where our map is pointing. So we just need to determine the risk category here, which is set to risk category 3. And ultimately, the program is giving us a basic wind velocity of 130 miles per hour, again, coming directly from the ASCE 7. So just a useful tool if we're trying to figure out quickly what this wind velocity should be. We convert this to feet per second, and we're going to get 190.67. So based on all of this information here, our wind profile is going to update automatically. So we don't need to do anything further. We can also see it graphed out on the right-hand side. The second tab I've already briefly mentioned is just listing out the various wind load cases depending on which direction our wind is coming from. We'll get back to this in just a minute. The third tab is the settings for the CFD analysis, and this is a little bit more theoretical than what we've seen so far. So The flow parameters for the air density and kinematic viscosity must be defined. So it depends on where your project is located, especially with elevation. The defaults here are relatively close to maybe something you'd find at sea level. So we can just leave those defaults here, but certainly determine what your air properties are for density and viscosity for your project, and you'll input it here. The calculation parameters. So this includes the density of mesh for the fluid dynamics calculation. This is used for that model simplification that we talked about and the fluid calculation to control the finite volumes around the structure. So we'll see this in a minute, but this is in reference to the actual wind tunnel itself and our 3D finite volumes. The default here is 20%. The range is anywhere from 10% to 100%. Obviously, 10% is the most coarse, with 100% being the most precise. But keep in mind, when you set this to something like 100%, the calculation time could take anywhere from several hours to several days. So you want to maybe determine here, okay, what's a good balance that we're not waiting so long to get our calculation, but that it's providing accurate results. For today's example, we're going to set this to 10% just to get a quicker calculation. The max number of iterations is useful to avoid infinite loops within the calculation process, but keep in mind that not all iterations have to be carried out. So if we find convergence before this 500 has been reached, the program will present our results to us. So we'll just leave this as the default. The convergence criteria is the stop limit for the calculation. So when the residual pressure has fallen below this defined value, then the calculation will stop. Again, the default settings 0.001. You can go smaller, may take longer to find convergence. If you go too big, then you may not be getting accurate results. The level of detail, this refers to the structure itself and this mesh shrink wrapping. The range is from 0 to 4. So if you can remember back to the PowerPoint with the flower model, we're talking about, okay, how much detail at the center of that flower do we want to consider? Do we want to really simplify it, or do we want our mesh shrink wrap to really account for every single detail? So therefore, with this range, 0 is the most coarse and 4 is the most fine. Default here is 2, but I'm going to set this to 1. We have, again, a very simple structure for the most part for today with not a lot of detail. The number of the first load case to be generated is by default set at 2. The only reason that's set at 2 is because I've already defined a first load case here for my self weight. If I had more load cases defined, then this number would be increased, and you can control it yourself as well. The turbulence model properties refers to chaotic changes of pressure and flow velocity. So we can consider turbulence by setting a turbulence intensity percentage here. This also has a range with 0%, meaning there's no fluctuations in the airspeed. When we look at a range of 5 to 20%, this is highly turbulent cases. So we found that 1% essentially covers most medium to low turbulence cases, but again, you'll want to adjust this turbulence intensity as you see fit. Now, the other option you have is to specify the K epsilon terms independently here. This is for elevation independence. Otherwise, the program will go ahead and determine that underneath the hood by the turbulence intensity percentage. The member load distribution. So you can remember that I mentioned not only surfaces that are possible, but of course members are possible to consider within RWIND. The program is asking us, when we bring back in these generated wind loads from RWIND, how do we want them to be distributed within RFEM as concentrated, uniform, or trapezoidal loads? So we don't have that scenario here, but that's essentially what you're choosing. And finally, we have our last two options. The first option is to export the optimized member topology. This is checked by default. And what this is in reference to, if we consider something like a I-beam that has flanges and a web, when this option is checked, we'll actually just export a basic rectangle shape or a basic square shape to simplify that section geometry. And most likely it's not going to impact your loads enough. But by all means, if you would like to export out the exact geometry of these cross sections, then you could uncheck this here. This checkbox to export active objects only refers to if we had some other elements back in the RFEM model that we had modeled that we didn't want to be considered for the wind load, well, we could deactivate them. In our case, it doesn't matter whether we check this or uncheck this because we only have one structure. Okay, so back under the load cases here, we are now ready to begin our calculation within RWIND. The most efficient option would be to choose this button here that says calculate all in background. So what essentially will happen is that RWIND will never open. Everything is going to happen behind the scenes. The program will run that calculation, and then eventually we're going to get checkboxes here for calculated, and the load cases will automatically be available to us within RFEM. Now, on the other hand, if you're wanting to see the actual calculation within RWIND, which we do today because I want to explain several of the program features, we can place our cursor on any one of these wind directions. Now, these angles are based off the global x-axis, and this is true in either program. The x-axis will be oriented in the same direction. So when we are considering wind from the 0-degree direction, we're going to have wind flow from left to right on the structure here. This structure is at a skew, so I'm not going to have wind directly on the front face, normal to the front face, but rather it's somewhat of an angle here. So it should be quite interesting to see once we get into RWIND. And then of course, we're just going to move around in a full 360 circle until we have fulfilled all of these different load cases. So for today, let's just consider the 0 load case, and I'm going to put my cursor in that cell, and I can open RWIND simulation. So you'll notice that within a split second, my structure geometry is imported into our standalone program, RWIND. And we can zoom in here to view this structure, and the model geometry is quite exact. It includes that double curvature front surface here. You'll notice that we also have our opening located up here at the top. So everything would be brought in directly from the program without having to select any further modifications. The first thing I'm going to do here is to activate my wind tunnel, and I can do so under my display options. So here exactly is our wind tunnel that we're going to run this numerical CFD analysis. If I change my view settings here to the reverse Z direction, I'm now looking at a plan view. So we can see my structure. As I mentioned, it's located at kind of a skew in relation to how the wind flow is going through this tunnel. So we can see by the big red arrow, the wind flow will be from left to right. You'll also notice the meshing of the wind tunnel itself. So this is what we have set with the density of the mesh at 10%. When we're on the exterior here of this wind tunnel away from the structure, it's quite coarse. But as we move in closer to the structure, then you're going to see a more refined mesh. All right, so going back to the isometric view here, let's take a look at the simulation parameters. So I'm going to double click the option over here in my project navigator, and quite realistically, this is all of the information that I have already set within RFEM, but I do have the ability here to make any changes if I'd like. But just know that we don't need to repeat any of this information. It is brought in from RFEM. So for example, we have the flow parameters, which includes the inlet velocity, which is the wind speed entering the tunnel. We also have the kinematic viscosity and the density of our air. Remember, we left those at default. We also have the finite volume mesh settings. We had set this to 10%. You'll notice that as I use this slider bar to increase this, how my mesh is changing on the right-hand side. We're increasing the number of 3D volume elements for an increased mesh total. So again, that's going to change quite significantly. So you can imagine when we're all the way at 100%, these 3D volume elements, why it takes such a significant long time to run the calculation. These mesh cells are only 1.8 feet wide, and keep in mind this structure, although it looks small, is about 480 feet high, which was modeled in RFEM. So we will go back to the 10% here for a mesh cell size of about 18 feet. The calculation utilizes the OpenFOAM numerical solver. As I mentioned, we're working on more solvers in development at the moment, so this is the one that we'll be taking advantage of. The max number of iterations and the convergence criteria, 500 and 0.001 that we brought in from RFEM. Same concept for our turbulence tab. Here we have set the turbulence intensity to 1%. You'll notice that the turbulent kinetic energy, the turbulent dissipation, and the specific dissipation are all calculated automatically by the program. If we change this to 5%, again, you'll see these numbers change. We'll just be going with the 1% that we previously set. And finally, we have our wind profile here, which is again the information we set according to the ASCE 7, and it's simply the wind speed as a function of height as we move up along the height of our structure. We can make changes to this here as well. So I'm actually going to hit cancel because we want to leave everything as we've previously defined it. Similar concept for our actual model here. Under the model tree, I can double click and I can see a few of the settings displayed brought in from RFEM. One thing that we didn't specify in RFEM is that this is the primary model. The program automatically recognizes this and puts a checkbox here. A little bit later on, when we consider adjacent buildings, you'll see how this differs. The model simplification is set to 1 for the level of detail. And let me also quickly mention, you see this checkbox here for the simplify model. Remember, I said you do have the ability to turn off the model simplification, but it is only suggested for advanced CFD users. So the level of detail, we have set this to 1 for our example today, just for a pretty quick calculation. We don't have much detail that we're worried about. We also have the openings that can be closed for any distance that we specify here. So we will not be making any changes here, so we can click cancel out of this. I just wanted to quickly go over it. The final thing to discuss before running our calculation is the actual wind tunnel itself. So I can double click the wind tunnel settings. And you'll notice that the dimensions of the wind tunnel are defined with 2 different points. We have a point located at the upper right corner and the lower right corner and the upper left corner in the back. So that will define this rectangular wind tunnel for us. Now, if you want to make any changes here, you can. The program automatically adjusted this wind tunnel based on the structure we're bringing in from RFEM and its geometry. But if I've decided I want to extend this wind tunnel to maybe 4,000 feet in the back, I can just simply type that in. I can hit apply, and now you'll see that my wind tunnel is extended. In a similar sense, we have the ability just to adjust this tunnel graphically as well. So we can choose this option here. And now we have arrows that just allow us to slide in the dimensions here, whether that's at the top or bottom, the left or right, and that will automatically adjust our wind tunnel. So going back to the wind tunnel settings, if I have messed around too much with my wind tunnel and I just want to go back to the suggested size that the program has, we can just click this option, adjust to model, hit apply, and then we can see now we're back to the original settings. Okay, so we are now ready to run our calculation. So we can click calculation results in the edit bar. And essentially, the program's giving us a quick update list here of what exactly is happening, including the number of mesh cells. It's applying that shrink wrap mesh to our model. And it's also going to account for the closed openings, the level of detail, all of those parameters that we've previously set. I did want to mention too that the OpenFOAM solver that I mentioned is an extremely powerful tool for not only wind calculations, but also for fluid and for heat. But with that said, all of the internal options within our wind were actually created with wind loading only in mind for the structural engineer. So although the OpenFOAM solver has those capabilities, maybe in other programs, it does not within our wind. You only want to use this program for wind calculations only. So once we are done with the analysis here, the program gives us this option and it says the calculation is finished. Do we want to close our wind? Yes or no. And when we close our wind, the results will automatically be imported into RFEM, which we'll see a little bit later on. But for now, let's take a look. Let's click no and take a look at our results that are available to us in our wind itself. So the first thing I can do here is I'm going to deactivate my wind tunnel so we can see this a little bit more clear. We'll zoom in here. Also, under the View tab within the Project Navigator, the interface is set up quite similar to RFEM for those of you that are familiar with it. Under the View tab, we can deactivate and activate different features that we're currently viewing in the graphical interface. For example, I can expand the model tree here, and I can activate these triangular edges. And this just shows me my mesh, essentially, around my structure. And I think this clarifies a little bit further what's going on with these wind pressures. So we're currently viewing the results here for surface pressures on the structure. You'll see that as I move my mouse around on the structure, I'm actually getting the pressure magnitudes given to me, and the colors are based here on the magnitude shown in our color navigator over on the right-hand side. So we can see even down into that opening how the wind is affecting our structure. We can also take our structure and completely rotate to the back side here, and you'll notice that a negative value is given. This means that these are no longer compression forces, but these are the suction wind forces at the rear of the structure, with the highest suction forces in the lower right-hand corner. So ultimately, what we're seeing here is the final results from the CFD calculation on our structure only. What we can also view, though, is what's called the pressure field. And this is a plane which represents the wind pressure distribution of the airflow throughout the wind tunnel. So not necessarily just on our structure, but throughout the entire wind tunnel itself. And you'll notice here with the pressure field, I can just simply drag this plane from left to right to see what's exactly happening within this area around my structure. In a similar sense, we can even change the plane here, and we can drag this now from top to bottom to view those various pressure fields. One thing to point out is I said that this is throughout the entire wind tunnel, but it looks like it's really only isolated around the structure. And that's because we have this option here checked to show the reduced domain. When I uncheck this option, now we're seeing the pressure field throughout the entire wind tunnel. We're making the assumption, though, that you're probably most interested in the results closest to the structure way out rather than way out here within the wind tunnel. So that's why we've given you the option to show the reduced domain. The pressure is given here, of course, according to these various colors. You have full capability to change units within the program. So right now it's given it to us in PSI. If we want to make any changes, you can find that under options and units. In a similar sense, we have the velocity field. So we can activate the velocity field, and just similar to the pressure field, it's in a two-dimensional plane here that we can kind of move around our structure. What also might be interesting with this is to change the plane once again to view what's happening at the rear of the structure with a lot of those suction forces. Again, all magnitudes are given here in miles per hour as a function of color. The velocity vectors, and for this I'm going to completely deactivate my wind tunnel so that we can see this a little bit more clearly. The velocity vectors is going to evaluate both the wind speed but also direction. So now you're going to see arrows here showing us exactly in which direction the wind load is being applied. Again, changing planes here to maybe our horizontal plane. We can take a look at in more of a plan view of those not only magnitudes, those wind speeds, but also directions. And finally, this leads us to streamlines, which is probably going to give us the best effect for understanding our wind loads here. And streamlines are a composition of curves which are tangent to the velocity vector. Essentially, this is going to show the direction which a massless fluid element will travel at any point in time. And again, these colors are varying by speed. And similar to just showing the streamlines as a static view here, we also can activate the streamlines animation. So again, a great visualization here, a nice video showing us these wind forces acting on our structure and how exactly those massless fluid elements are moving. If we want to export these videos, we can do so under Tools and Create Video File. Of course, this is extremely beneficial to send with your calculation package or to any review engineer just to view how those wind loads are being applied. So we can deactivate this animation here, and I want to go into a few more options within these streamline settings because it is quite powerful what we have the ability to view here. The default is a 3D box, which we can see here. Now, similar to the wind load tunnel, we can, grab this 3D box, move it, increase it, decrease it. We also can decrease the number of points. So it's pretty overwhelming right now. Maybe we want to decrease those. We can hit apply. And we hit OK, and now we have quite a few less streamlined particles to show. Again, just making that video maybe a little bit more clear on what's exactly happening. Going back to the streamline settings, not only do we have the ability here to define a 3D box, but we have several other settings, including a segment. And a segment is going to be just a particular line. Now, again, you can drag this line up and down, left and right. Perhaps we want to increase the number of points significantly here. I can hit apply, I can hit OK, and now we can see how those streamlines are moving throughout our structure at just a single line element. So again, just different ways to manipulate this view so that we can view exactly what's happening at different locations. What's also nice about these streamline settings is not only does it need to necessarily be in a horizontal line, but we can actually rotate it vertically here. And I'm just going to eyeball this, move it over to the right of the structure a bit. And sorry, let me do that again. Move it in the vertical direction. We can move it over to the structure. We can hit apply, and maybe we move it a little bit further over to the right. We hit OK, and now we can see it in the vertical direction as well. So again, many options here, and of course this is endless, but you can add these to printout reports. You can export these streamline animations as video files as you see fit. So ultimately with these results, if we turn off our results, let's activate our wind tunnel again. Maybe I turn off this triangular meshing. We have only analyzed the structure within this wind tunnel by itself. And if you remember back to the PowerPoint, I said a very powerful feature of CFD numerical wind analysis is to account for complex terrains or adjacent buildings. So how do we do this? Well, under the Data tab, what I can do here is to right-click on the model to import a model from File. I want to account now for some adjacent buildings that will be located right next to my project that I know are definitely going to influence the wind load. So we have a few file extensions which are still in development, but what we do have available to us is an STL file. So for example, I use SketchUp, I exported my adjacent structures as an STL file, and now I can easily just import them here, which we can find directly on our computer wherever we have saved it. I click open. I am going to adjust the wind tunnel dimensions, but I am not going to move the imported model to the origin. I'll actually make a few movement changes once I import. So when I click OK, the program says that my results need to be deleted, and I click yes, that's fine. So now let's deactivate our wind tunnel here, and I zoom in. I now have some adjacent structures to my original structure. Now the location of these is not quite right, so I can either take this and just simply drag and drop it wherever I'd like, but probably the more accurate method is to double click, and you'll notice here that neither option is checked. The primary model is, of course, our model that we brought in from RFEM, so we don't want to specify this as the primary model. If this was a terrain STL file, we would want to modify this so that the wind tunnel itself would be modified. But rather, this is just some adjacent buildings. We want it to influence the wind load, but it's neither one of these, so both can be left as unchecked. But under the Positions tab, this is where I can modify the origin of this imported file. And for today, I want to modify to a negative 120 feet in the X and negative 950 feet in the Y. I click apply, I can hit OK, and now we can see how these adjacent structures sit right next to the building in question. So inevitably, this is why I want to account for these adjacent structures, because I know that the wind loading is going to be affected based on where these are located. And you can imagine that when we start to consider wind loads, especially in the 180-degree direction, it's going to be significantly impacted by these rear structures. The wind tunnel, when we first imported in this additional file, the wind tunnel was automatically updated, but then I moved these adjacent structures around a little bit. So remember, all I need to do is to double click on the wind tunnel, adjust to model, I click OK, and now my wind tunnel is slightly smaller here, and we are now ready to begin our calculation. So I can calculate my results, and you'll notice a couple things here. That first of all, we have a little bit more mesh than what we were previously dealing with, and that's for a couple reasons. Of course, we had to increase the size of our numerical wind tunnel here to account for the additional structures. We're also going to apply a mesh shrink wrap around these adjacent structures as well. But eventually, as soon as the program is done applying this mesh shrink wrap to not only the adjacent structures, our structures, and account for the 3D volumes here, we're going to get essentially a pressure diagram. And what this pressure diagram is going to show us, which you can see residual pressure as a function of the iterations, it will show us the progress of the applied pressure during the iterative simulation process. Remember, we set our convergence criterion to 0.001, so the program is reaching to find that. The solver will start with an initial pressure value, and then the simulation refines the residuals with every iteration. Ultimately, it's trying to reduce the pressure imbalance. So if you find the scenario of looking at this graph as it's solving and there's a lot of oscillations, that's probably means that there's not great convergence, and we need to make some changes to our model. One change that might be helpful is to increase the length of our wind load tunnel. Sometimes the wind load tunnel is too short, and by increasing that, we'll get better convergence. We could make some changes to the meshing, whether it's the density of the wind tunnel or the details of the structure as well. So quite a few changes in order to find better convergence. Ultimately, though, we are presented with our results here. We do not want to leave our wind quite yet, and we can take a look at our results presented to us. So let me jump to surface pressures, and we can see the high surface pressures at these adjacent buildings, which are available to us. But ultimately, we're looking at how these adjacent buildings impact our structure that we're designing. And you'll notice that in some locations situated behind this adjacent building, I'm getting extremely low pressure values, clear up to 0.008 psi, where previously we had fairly high pressures there. So that's how these adjacent buildings can impact our wind loads themselves. Now, ultimately, there really is no reason to go through the rest of these results. It's exactly as we just covered. We have the ability here to view all of the results just like we saw before, but now considering the adjacent structures. So what I'd like to do is to exit out of the program, and notice it didn't ask me to save, it asked me nothing, and that's just because everything is brought in from those wind loads into RFEM. So we're back in our finite element analysis program, RFEM. You can see that the calculated checkbox is now activated here. I can click OK. And not only do we have self-weight, but we now have a second load case for wind in the 0 direction. Now, I can activate these loads. Let's turn this into a rendered view. And it's quite overwhelming if we take a look at wind in the 0 direction, and that's just because we're bringing in all of those wind loads and applying them to every mesh point here in both the X and Y direction. So underneath the hood, that's what's going on. Like I said, a little bit overwhelming, so we can deactivate those loads. And what we can do is just to run a quick calculation here of only this particular load case in the 0 degree direction to see what our results look like. So quick linear analysis, and ultimately we'll be presented with our results in RFEM. Maybe I want to take a look at the deformation, and I can see here that based on my high suction forces in the rear of the structure, high compression forces at the front, I have some deflection that looks similar to what we're seeing here. What else we can view is the feature here under the distribution of load, which was just added, and it's wind load using RWIND Simulation. This allows me to view the wind load distribution that we brought in from RWIND for this particular load case. So for example, I can view the approximate distribution of load in kips per square foot or whatever units I have it set to on my structure. Now this is according to the global X, Y, and Z axes here, which those global axes are displayed in the lower left. We can change this to the Y view, our global distribution of load according to the y-axis. Again, this is where we're seeing those extremely high suction forces on the rear of our structure. Ultimately, too, we can view load distribution based on a surface's local axes. So, for example, the y-axis is normal to the face of these surfaces, and local axes are indicated by lower x, y, and z. So if we're interested in viewing load distribution on each individual surface relative to the local axes, we can do so. So what's so powerful, again, is just getting the realistic wind loads for these complex geometries. We can even see down in the opening of this structure here exactly what the wind load distribution looks like. And essentially we have no wind load down in the bottom, but then we're going to have fairly high wind pressures when it comes to the upper inside surface. Now we have imported in this single load case. I just wanted to point out, if we go into our load cases and combinations, we have our self-weight, we have our wind load here, which we can change the action category to wind. What we can do within RFEM is to create a load combination. So we create our first load combination combining both the self-weight as well as this wind load case. Now you can imagine we can also combine live loads, snow loads, any other particular load case. And this is what we can solve for within RFEM to get an analysis considering not only the wind loads but all other load cases. And eventually we can move into design as well the structure within our add-on modules. So quite powerful in the sense that just importing in a simple load case for wind load, and we can go about the analysis and design as we normally would. Okay, so that concludes the webinar for today. We do have much more information on RFEM as well as RWIND Simulation available on our website at duluwal.com. We also have our web shop available, so if you're interested in how much this program could cost, feel free to visit the website and take a look, because we're completely transparent with all of those costs. I also want to encourage everyone to follow us on our social media accounts. For example, our YouTube channel has previous videos and recorded webinars similar to the one that you're viewing today, so you can watch that at your own leisure. Also, our other social media sites, LinkedIn, Facebook, Instagram, will go ahead and give you just up-to-date information about events and conferences we're at, maybe new technical articles and FAQs that have just been released, so it can be extremely helpful. If you have any questions about today's presentation or anything else, feel free to contact us in our Philadelphia office at info-us@duluwal.com, and the phone number here is 267-702-2815. So we will have many more upcoming webinars. I try and do these about once a month, so the next webinar will probably be sometime in January. You can register on our website at duluwal.com under support and learning and webinars. As most of you know today, though, that I typically send out a reminder email about a week before these will take place, so feel free to register through there. Many of you are wanting PDH certificates for today, and that's no problem. These will be automatically emailed to all participants who were here for the full presentation. So that is a requirement from the various states that you are here for the full presentation duration. Now, I will say that if you did watch this webinar today and you did not register yourself with your own name and email, but rather you're watching with a colleague, for example, then you will need to request a PDH to the email shown here at info-us@duluwal.com. Again, if you yourself did not register with your own email and your own name, we do need you to request the PDH at info-us@duluwal.com. With that said, I want to thank everyone as always for attending, and we hope to see you at our next webinar. Thank you.